Good evening. Welcome to Empower You. I'm Diana Tellis, Empower You board member, and I'm eager to introduce tonight author Mike Conley. Mike and I will discuss the future of clean energy. He comes to us this afternoon from Los Angeles, California, which is probably not exactly the hotbed of nuclear fandom, but we'll find out more about that. So let me introduce author Mike Conley. Fascinated by science since he was a child, Mike was drawn to the ingenuity, simplicity, and the safety of the molten salt reactor, which are referred to as MSRs. To learn more, he became a member of the Thorium Energy Alliance, or TEA. It's a close-knit community of MSR advocates. His approach to the brainiacs that he met through TEA is simple. If they explain their technology to him, he'll explain it to the world. Mike's 4 books are the product of that ongoing project. He considers himself an uncredentialed expert. Welcome, Mike, to Empower You.
Hi, how you doing?
Glad to have you tonight, or this afternoon for your case, right?
Yeah, no, it's great. It's great. Yeah, let's rock and roll. What do you got going on?
Well, your work is very much appreciated by me, Mike. I have learned a lot across several years, many years, in discussions with my science-minded husband. In fact, I was a little bit tempted to have him here tonight, right here, because he understands it way better than I do. But he has dispelled fears that I've had about nuclear energy, and I'm lucky to have him as a resource, and not everybody does, right? And I do see it as part of our energy future. It's clean, it's abundant, and it's affordable. But I also know all too well the power of messaging, misinformation, and disinformation is where the danger truly lies. It gets in the way of progress, not to mention, I can't even imagine the power of the petroleum lobby or the, big oil. But bad messaging and the imposition of unfounded fears in the public would seem to be the greatest risk to elevating nuclear power as the nation's main source of energy. And you wrote a book called, I'd like to start with this because I heard you do this on another recording that I watched of you. You wrote a book called, you've written several, but the one I'd like to refer to right now is called Earth as a Nuclear Planet. Can we start with your explanation of why Earth is a nuclear planet?
Well, it's actually pretty simple. The reason why Earth is a nuclear planet is we have a molten outer core. Well, how did it get that way? Half of the heat in the core comes from radioactive decay and a bit of fission. And then the rest of the heat is from, I think, the original construction or formation of the Earth. And it's almost all iron. So it's molten, and because the Earth spins, it spins. And because we have a rotating blob of iron, it creates an electromagnetic shield around the Earth. And that's what deflects the solar wind away from the Earth so it doesn't rip away our atmosphere. As a consequence, we have a breathable atmosphere. So if we didn't have nuclear material in the core, and it's also on the surface of the planet, we literally would not have an atmosphere, a breathable atmosphere, and we would simply not exist. Cellular life might very well exist, but we never get to the oxygen part, which happened about 2 billion years after cellular life began.
So nuclear isn't always a bad word.
No, I'm
just looking at it from the perspective of the public, right?
Oh yeah, okay.
And after Fukushima in 2011, I heard Charles Krauthammer say that nuclear power was dead, and I was shocked to hear him talk like that. And you say that people have an irrational fear of nuclear energy. In fact, like literally just on Sunday, the Plain Dealer had an article highlighting the troubled past of an Ohio community that has been dealing with a poorly managed uranium enrichment facility that was operating during the Cold War. So I don't want to dig into that, but like it's things like that people have on their minds. They're dramatic and they're awful, and that was clearly irresponsibility. Can you give the audience a primer, though, for the lay person, like comparing the types of nuclear technology that you put your faith in, which I presume is the molten salt reactor, if I understand.
Molten salt reactor is my favorite reactor.
Okay. So then And I presume then that's like the up and coming technology. Then we'll be seeing. Okay, so then to the general public envisions based on history, Chernobyl, Fukushima, and military explosions, right? Military grade weapons, which is quite
Bombs,
different than
right.
what we're talking about. So can you, for the layperson, like explain nuclear technology right now as you envision it as this wonderful way for us moving into the future? What technology is that?
Well, the molten salt reactor was actually, God, it was invented back in the 50s, and it was tested thoroughly at Oak Ridge National Labs in Tennessee in the 60s. I think 20,000 hours of full power operation with 3 different fuels. And the saying was that the hardest thing about their experiment was finding something to do, because the reactor ran itself. It regulates its own heat temperature without operator adjustment. It cannot melt down, and you're not going to have a downwind fallout cloud because it doesn't use water; it uses molten salt. Nuclear fuels are metals: plutonium, uranium, thorium. They're metals. You can make a salt from a metal. So if you have a batch of salt and then you throw in some nuclear salt, and you put that batch of salt in a confined space, it'll fission. When you take it out of that confined space, it stops because what's called the fuel geometry isn't right. It has to be in a kind of a spherical shape so it can bombard itself from every angle, because they only put a certain amount of fuel in. So as soon as you take that, and when the salt undergoes, when the nuclear fuel and the salt undergoes fission, it kicks the temperature of the salt up another 300 degrees, which is fine because salt melts at 400 Celsius. It boils at about 1400 Celsius. And the reactor the fusion kicks it up from about 400 to about 700. So you're still like hundreds of degrees away from a boiling point. Okay. So it's sort of a pot that never boils. Okay. And the lid's always on. And when a stream of it is taken out of the core, fission stops like that because it isn't surrounded by other fuel. It's simply just a hot salt, radioactive, but it's not fissioning. And then it goes and does its work, whether giving up heat to an industrial process or giving up heat to a steam generator that can make steam to run a turbine, et cetera. And then it cools as a consequence and comes back. And the nice thing about the salt is when it cools, it shrinks. When it heats, it expands. When it shrinks, fission increases. When it expands, fission decreases. So it always has a Goldilocks effect that's always in balance with no operator control, okay? And so as you draw heat from the reactor, it produces more fission, thus more heat to replace the lost heat. As it expands, the particles move away from each other, reducing the rate of fission. So it's just it's a ingenious design. And the thing is, it's not using pressurized water, which has been the problem or the drawback of earlier reactor designs, is you have to keep the water under about 18 atmospheres of pressure to keep it liquid at that temperature. So it works sort of like a steam boiler where you have a heat source. This time the heat source is inside the boiler, a solid fuel reactor. And then you run pressurized water through it. It picks up heat, gives off heat, condenses, picks up heat, etc. The molten salt reactor does the same thing, but it's not pressurized water. It's unpressurized molten salt. Visualize candle wax. Really, really radioactive candle wax. Okay. But it's not, if something happens to the reactor, it's not going to go anywhere because there's nothing forcing it into the environment.
So there's no radioactive steam then, right?
No, not at all. There may be fresh water steam from the turbine that makes the power, but all this reactor is doing, this is actually how it works, is you have the radioactive loop of molten salt. It heats a non-radioactive loop of clean salt, solar salt, the same they use as solar thermal storage, right? So radioactive salt heats clean salt. It doesn't radiate it, it just heats it. And then that clean salt is used to make water. And so if something happens, whatever steam release is way at the other end of the plant, the reactor's not affected. And because it is not pressurized, if let me back up a second. The way you stop the reactor is you drain it like a bathtub. And the molten salt goes into several small holding tanks. Okay. If that mechanism fails, and let's say somebody lobs a missile at the reactor or something like that, or let's say that the reactor somehow malfunctions, at the worst, what would happen is the salt will start heating up, the metal walls would get soft, and the molten salt will spill onto the floor and cool and solidify. So what you'd have is a messed up reactor room and not a messed up county.
Right.
And then it cools off and you send in robots to clean it up. And there you go. It's really a simple design. It was invented by the same people that invented the light water reactor, the pressurized water reactor. And it's a far superior design, but the light water reactor became so popular so quickly that it became the world standard for power production, and the MSR was forgotten and shelved. And then in 2006, true story, the research material was no longer classified. The Chinese came over, took a tour of Oak Ridge, and they were interested in the molten salt reactor. They got all the data, and they went back to China, and now they're testing one in the Gobi Desert. So, I mean, China is making our own invention, and they didn't steal the information. It was given to them because it was classified and considered, well, yeah, that thing, whatever. Oh, they're interested in that? Okay, give them the data. Who cares?
It's very interesting you bring up China, because that's another reason we would need to employ nuclear in the future, because in order to keep up with China, we would need, manufacturing wise and efficiency and cost per kilowatt hour. I know it's a lot, and eventually we'll get there. We wouldn't be able to compete if China's gone fully nuclear in their energy.
They can build 50 reactors at one time now. That's how big their infrastructure is. And we have to build that up to do the same, because in our third book, Roadmap to Nowhere, we calculated that it would take, at an average of 500 megawatts per reactor, it would take about, what did we figure? 1,300, 1,500, about 3,000 reactors of varying sizes, little small modular reactors, SMRs, and a couple of big jumbos, but all averaging out about 500 average. It would take about 3,000 reactors. We can build it. We have the technology. We no longer have the skill, because it's a forgotten construction methodology that we tried to just run up the speed and do at Vogel in Georgia. And it was a mess because our supply chains were insufficient. Nobody had any experience. They were building on top of that, they were building a brand new reactor design instead of something we built before. And so basically, America has got to get its act together on how to manufacture big ticket items at scale, which is completely doable. We built, in 1944 at Willow Run, they were building one B-24 per hour. We built 3,000 Liberty ships, no computers, no cell phones, slide rules. 2,600 of them were floating at the end of the war. So we can do big stuff, but we haven't been doing it.
Well, we have public opinion as a problem, and regulation, I presume, is a terrible problem. China doesn't have to worry about regulation, right? They just do whatever they want. They don't have to.
Well, yes and no. Yes and no. They have to build, and they are building to IAEA international standards. The regulations, though, for example, in our country, a company has to spend about $1 billion just in the paperwork to get a license to build a reactor.
Wow.
Okay.
Yeah.
China doesn't have that.
No.
Like, for example, the Oklo reactor, a molten salt reactor, actually it's not molten salt, it's a sodium cooled, it's another similar. And they said, hey, we're just rebuilding something that ran successfully at Idaho National Labs for 30 years without a fault. Mm-hmm. And in an emergency test, they shut off all power to the facility. The reactor got a little warmer, then shut itself down by itself. And they go, hey, we want to rebuild this. And the NRC, the Nuclear Refusal Commission, is like, okay, here's a bunch of paperwork. You got to fill out 12 million pages. I'm not kidding. Millions of pages.
Commission, I assume you made that up.
Oh, thank you. And and it cost them $1 billion. just to
right.
get to the point where they can build a reactor, and luckily Bill Gates has the money to do it, and he did it with the TerraPower
Right.
reactor.
Right.
Aklo, I mean, God, they had a dig deep in their pockets, and it's ridiculous. On top of that, the NRC reserves the right to change your plans and make you redo stuff in the middle of your
Right.
build, which happened after Fukushima, which was freaking stupid. Fukushima, which we can get into in a minute, happened, and the NRC said, "Oh my God, Vogel, you'll have to redo your reactor to make it tsunami proof," and it's 300 miles upriver. Okay, and so the thing is we have to make our regulations sensible, and we have to build up a supply chain and a work crews that are experienced in building it. And my suggestion is, until we learn how to do it right, let's hire the South Koreans who can build one of their APR 1400s on U.S. soil. It's approved for build on U.S. soil. It's just a big old jumbo light water reactor. It's a big V8. It's a big V8 engine, and they are building them routinely in their own country for around $3,300 an installed kilowatt. Vogel,
So they're expert level. They're there.
Yeah. So if we want to get into doing it, why don't we just hire people that know what they're doing, and we literally pay them and watch them?
Let's revisit that, because I bring this up a little later on about some of the messaging, and it was messaging that I saw on your webpage, and we'll go back to that. I want to pull it back for the moment, because SMRs are kind of so small modular reactors. And then I saw, just when I thought I knew it all, I saw on your one chapter of your book that you shared with me, there's even a micro modular reactor, I think it was.
Yeah, there's micro reactors. Rolls-Royce is building one.
Well, what are those? Like, what are they? And they feel like they make me feel good. I think, oh, good, good. We can stack them up. They're little, and then some of the things you've already talked about with regulation and with putting $1 million into just the planning, and us not really knowing, like, having the expertise at this point, and how complicated that is. An SMR suddenly makes it feel like this is something that's more reasonable, because when we build them, we're not going to get to this big, giant, production nuclear plant, and then find out after it's built that we did it all wrong, or it didn't meet this, and it's over. So these smaller ones are less risky, I presume, and there's less paperwork and less regulation. So how in the world do they work? I mean, is this also, here's the question I wrote for you on this. It's, let's talk SMRs, the efficacy. Like, should we expect to see these in the near future? I think we are. A combination of full size, or is that the future, or is it a combination of, like, traditional and these micro? What are we in for? Because there's
a lot of evolving designs, and to try to make it simple, a small modular reactor is a small reactor that can be built in the factory in modules and assembled on site. So, okay, hey, I want a reactor. Okay, I'll build the reactor at my factory, and you build the location for it to be, you build the plant, and then we'll come over with the modules and bolt it all together. The size of the nuclear plant, the small modular plant, would be literally about the size of a Costco. Okay. 300 megawatts or less, that's enough for 300,000 homes or something like that. There's some measurement I never paid much attention to, because you do a lot more than power homes with it. But anyway, the nice thing about small modular, there's several nice things about small modular reactors. Number one is the cheaper buy-in. Number two, they're modular. So literally every single part, including the core itself, could be replaced, which means, in theory, they could last for more than 100 years without a problem. If it gets old, you replace the core, or you replace the steam assembly, or whatever. And it's sort of like a boy band with no original members, You just keep replacing whatever needs to be replaced. Number two, it's a tiny reactor. It's on a postage stamp of land. As an example, you may have heard of Mark Jacobson's 100% wind, water, solar roadmap to power the entire U.S. with nothing but wind and solar, which is basically the subject of our third book. And that would take, with the offshore regions, 117,000 square miles. Small modular reactors and Gen 4 reactors would take about 375 square miles. about 0.5% of the land area. Because I threw in the water area, just the land area for the roadmap is something like 81,000 square miles. Anyway, long story short, the best way to produce power is you want to use the least amount of resources with the smallest amount of personnel, making the most amount of power in the smallest space with the least amount of waste, and do it 24/7 regardless of the weather. That's a checklist for molten salt reactors, for small modular reactors, and even for the big jumbo ones, we can get into the differences. Whereas wind and solar are entirely dependent on the weather, entirely. And you want us to spend how many trillions of dollars to build how much wind and solar for a future of unpredictable weather?
Right.
The idea, why make weather a part of the formula?
Right.
See? Right. And so the whole
variable, the
whole philosophical concept is nuts, because what they've done is they went, well, carbon fuel is bad, true, and nuclear is the work of the devil. So we have to look at something that isn't like a fuel. And so let's go back to the 1500s and play with windmills and go to a pre-combustion era instead of going to a post-combustion era to fission. Right. So they're retreating instead of going forward, and it's just bizarre.
Right.
And it's all predicated on nuclear fear. And then the enormous expense that comes on the heels of nuclear fear, and then a lot of specious arguments that can be dismantled, like that article you sent me, the Cleveland Plain Dealer. I read it and I'm like, well, that's true. That's not true. That's misleading. And it would take as long of an article to debunk the BS, sure, which is short for bad science. Yeah.
I believe you. So what I think people are I think it's coming, it must be coming back. So this small modular reactor, I don't know if it's, let me ask you this. Is the small modular, do they use salt? Is that salt used, or is it different?
No. Okay. There's two main kinds. One is basically a miniature light water reactor.
Light water. Okay.
But it's advanced and it's a tall, skinny reactor.
Is that a slow?
What's that?
Is that slow?
Slow neutron?
Yeah.
Yeah. So it's a regular, take your regular big old jumbo light water reactor and shrink it down to miniature size. Okay. And make it really tall and skinny. What happens is it now has internal passive cooling. What does that mean? It means it heats the water, it rises to the top, gives up some heat, and comes back down, convection. So the heat dispersal is through convection, number one. Number two, with a smaller core, you don't have the possibility of a melt through. Okay. Which is worse than a meltdown. A meltdown is when the fuel melts because it overheats. A melt through is when that blob of what's called thorium heats its way or melts its way through the steel of the vessel. A smaller core doesn't have the energy to do that. And the inventor of Alvin Weinberg, the inventor of the light water reactor and the molten salt reactor, pointed out that when you have cores larger than 600 megawatts of electricity production, you run the risk of the melt through. Okay. Small modular reactors are half that size. So you have a small container that it does not melt through. It is internal passive cooling. So if you don't need external cooling to cool it, like the municipal water supply, okay? And if it should melt down, it is a sealed container that can be removed from the facility and taken back to the factory with a new one put in, okay? So that's your typical small modular reactor. And molten salt reactors can also be made small, so they can be small and modular. In fact, ARC, Advanced Reactor Corporation in Idaho, has designed a 100 megawatt small modular reactor, and the entire reactor and its shielding. Imagine a 2-bedroom apartment and another 2-bedroom apartment stacked on top of each other. That's the total volume. Okay. About 30 by 40 by 20 or 30. Okay. And the safety zone is at the surface of the shielding. In other words, it's so safe that should something happen to the reactor, no nasties are going to get beyond the shielding. Okay. So it isn't like, you need to plan, you need to have iodine pills 50 miles away because nothing's going to get out of the facility. And if something should, it is small enough to where the steam release, if any, occurred, not with a molten salt reactor, but with a mini small modular light water reactor, the steam release is so mild that when it gets to the fence, it's not harmful. So you could literally watch a Gen 4 reactor nuclear plant in full meltdown standing at the fence. Okay.
Fascinating. That is fascinating.
Yeah.
And by far different than anything we're envisioning when we envision the worst. So you've been doing this about 13 years, maybe or so. Is that about right?
15. Yeah.
In that time, like for me, and I've been paying attention because I've been paying attention for longer than most. It seems like probably because of the data centers, this is now coming to the forefront. Like, I think we're going to see this. This is the real thing,
we're gonna have to.
Whether we like it or not, or whether, staunch environmentalists like it or not, but it's not just them. I mean, it's going to be, there's very smart people on both sides of this that are going to say, that are going to be suspicious because, and I can't say I blame, it's hard to trust, right? We have a very hard time with trust and with good reason.
Yeah.
But, so it feels like we'll have no choice but to accept this change and this movement into like this nuclear space, this new age coming of age technology. And then, I watched the State of the Union address, Donald Trump, and during that address, he literally addressed, because, our power is now at a premium now. It's very expensive. It's gotten more expensive because of data centers. And, people that don't even, use AI or even are being forced into paying higher prices because of the demand. And Donald Trump said that he will be, I don't know, I don't think it was a executive order or anything, but he was making the suggestion that anybody installing a data center would be responsible for their own power source.
Absolutely, 100%. I totally agree with them.
What else would it be? What else would it be than small nuclear modules? Because if they were to build their own little like generator or something using fossil fuels, they're still drawing from, our resources, and it's still going to affect the market, right? So it has to be small modular. It has to be. And
yes, it has to be. And they should absolutely be required to bring their own power with them and their own cooling, because they're like, well, we need your lake to cool. No, you don't. You just get a bigger reactor and run a bunch of air conditioners and leave us alone. If you want to be a good neighbor, why don't you come to the party with your own power and water, or your own power and cooling, should I say? And that should be, I think, a state law, is don't even think about, coming here unless you can show us that you can bring your own electricity and cooling. End of story. You figure it out. You want to come here? That's our requirement. Leave our water and power alone. 100%. And a small modular reactor can do that. A micro reactor for a smaller plant. Wind and solar cannot. Well, maybe it could if you have thousands and thousands and thousands of acres of it and a king's ransom and batteries in case the wind dies down or a cloud comes up. It's just, I think it's absurd to think about that much power with renewables. And again, I don't think renewables would have even gotten the traction they did if it weren't for an atavistic and misinformed fear of nuclear power. I'm sorry, but it's like, if uranium was as safe as chocolate pudding, let's just say that uranium was as safe as chocolate pudding, right? Would anybody even think twice about building out renewables? Unless you put solar on your roof is a great idea, but for your community, are you kidding? Really? You want to go through a hurricane and you go, well, we'll put the solar panels back in the field, reactors brush off hurricanes and tornadoes and that, especially if you put them underground, which is where they should be. It is an irrational conclusion predicated on a pile of misinformation.
So if I missed it, I apologize. But we got the small
micro reactor.
What's a micro reactor?
Just a smaller reactor.
They just get smaller and smaller. That's all.
It's a small reactor. It could be like 50 megawatts or 10 megawatts. Like I said, ARC in Idaho is building a 100 megawatt molten salt reactor, or maybe it's 10 megawatt. It was small. And so the terms are
Okay.
not hard and fast.
Okay. No, I mean, good. Then maybe that's what powers these AIs, these
Well, yeah, and also a large reactor is fine. The Gen 3 Plus reactors, the jumbo like 1,000 megawatt ones, they now have passive external cooling. It's really low tech. It's a big water tank above the reactor, and it mists water down, and it turns into steam and steams up, and then it catches in a cone and concentrates in the water and raises bed. It's really as low tech as that. It's just like, instead of relying on the municipal water supply, they just have this ginormous tank of water above the reactor. If you have a good hose, you're fine. It's not a complicated thing. And even like, you want to talk about Fukushima, I'd love to talk about Fukushima. Oh, there you go. Yeah. This is the PCCS water tank. I don't know why nuclear people love their acronyms. The water tank above the reactor. It mists down the steam. It turns into steam, comes back up and mists down again, etc. That should last for about 3 or 4 days, that tank of water. So if the reactor melts down or you got to shut it down, that'll last for 3 or 4 days. Then you fill the tank up with water again, and you just keep filling it up until the damn thing cools off. I mean, it's really not rocket science. The nuclear technology is rocket science, but the plant is basically no more complicated than a coal plant, except you're not burning fossil fuel, you're fissioning nuclear fuel. But the rest of it is basically the same. You're making steam to run a turbine, and that's it. It's just, boiling water, hot rocks, spicy rocks, as they say, Yeah.
All right. So back to the propaganda.
Mm-hmm.
So I saw on your webpage and in some of the YouTube videos I watched with you hosting or being interviewed, that a lot of your books, or at least one of your books, it's on your webpage, where talked about unfounded radiation fears. And I kind of laughed because we used some of that verbiage to promote this class. And I laughed when I read it back to myself after I submitted it, because it makes it sound like we're going to talk about, why radiation is, good for you or something. And it's clearly not. But I think your point is that the regulation and the fears are based on bad science. Can you tell us about that bad science and why it's Mueller, right? And why that bad science is hindering this progress, this energy source that we are in dire need of.
Right. 99 years ago, Mueller was a postgrad, and him and his fellow postgrads and their teacher were in a race to figure out how genetic mutations occurred. And if they figured that they can unlock the secret, whoever unlocked it would win the Nobel Prize. And so they were throwing all sorts of stuff at cells, poisons and gases. And Mueller's thing was radiation. Well, after I'm not exaggerating, 130 million times background radiation dose is what he was applying to these fruit flies. And they turned out weird, 4 eyes and green wings and red wings or whatever. And he's like, tra-la, I figured it out. And then he's working with his students when he's a professor, and he did 130 million times background. They did 40 million times background and 20 million times background, blasting flies. And they had a linear effect. In other words, more radiation, more harm, less radiation, less harm. Mueller extrapolated that straight line all the way down to 0 dose, 0 effect. He assumed the linearity will continue. 100th of the dose, 100th of the effect, 1500th of the dose, 1500, etc. That's called the linear null threshold. There's no threshold. There's harm at every level, but it gets less and less as you add less and less radiation, or more and more as you add. And that is just false, and is provably false. But he didn't have the instruments to prove his point, and no one had the instruments to disprove his point until decades later. And so he pushed this linearity, LNT, and it is simply bad science. It is not based on fact. It is based on an extrapolation of nasty things happening with high doses in a straight line to supposedly nasty things happening at low doses. And it has been proven not to be correct. But by the time it was proven not to be correct, regulations were ensconced. LNT was ensconced in regulations, and people took it as gospel. And there were like these science wars about this stuff. And Mueller was a very persuasive, very charismatic figure. And he kind of forced this on the scientific community. And a lot of people went along with him. But even if his best friend was like, how do you know you're not just blasting big holes in the chromosomes? Which it turns out, which is exactly what he was doing. Because a woman named Barbara McClintock finally figured out how to stain cells so they could see. You're not introducing point mutations, a little here, a little there. You're blowing big holes in the chromosomes with all these rates. And then his biggest mistake, his biggest sin, was extrapolating high dose effects into the low dose zone. Okay. And so that came into low dose. There's no safe dose of radiation. And then the other mistake he's made is saying doses accumulate. It's similar to microplastics. They accumulate. And you get enough in your body and bad things happen. That's how he viewed radiation. That one, cells cannot repair, which is not true. And two, since they can't repair, damage builds up. So there's no safe dose and it's linear. And the best solution is to have as very little radiation as humanly possible, which became ALARA, as low as reasonably achievable. And so LNT, linear no threshold, no safe dose, doses build up, and led to ALARA, the policy of making it as low as reasonably achievable. And as a consequence, you have the NRC going, well, if you spend another $1 billion on your reactor, you can get this radiation level from 0.05 millisieverts down to 0.005 millisieverts. And that is what has been happening and why it's been costing so much money, because people are trying to achieve ridiculously inconsequential levels of radiation. There's radiation all around us. I mean, you have radiation of potassium in your body. 0.12% of it, 0.012% of it is radioactive. It just is. And there's no way around it, because any potassium has, and if you don't have potassium, you're going to die. And so you have radiation in your body, and so they make all these like, well, that's how you get the damage, and that's why you die from cancer when you're 80. And oxidation results in much more cellular damage, far more cellular damage than radiation. And the mechanism the cell uses to repair itself from radiation is the same mechanism it uses to repair itself from oxidation. So saying all radiation is harmful is like saying all oxygen is harmful. Hold your breath. I mean, it's absurd. High radiation, absolutely. Absolutely.
So this bad science is still part of the narrative and has driven like the guidelines for regulation.
Yeah, my second book, the LNT Report, is a historical narrative of how this came to be, and it's written like a true crime story because it is a crime. And I wrote it to be a page turner. I write like I talk, so if people are to go, oh my God, I'm going to read a science book. Well, if you can listen to me, you can read the books, because my books are basically a long letter to my sister. Hey, Sue, check out all this cool stuff. And that's my writing style. And anyway, LNT Report is a true crime story about how this nonsense came to be and how it became embedded. There you go. Yeah, this is from 1957. Very quickly, this has to do with the radiation at the Hiroshima and Nagasaki, and the zones going from right to left, A, B, C, D, E, are the zones, the distance from the blast. And then this guy named Lewis in 1957, working off of Mueller's data, he combined the last two zones together to obscure that dip. And he's standing at the bomb blast edge of zone D going, oh my God, look, there's linearity. He's not standing where the not Lewis guy is standing, go, yeah, there's linearity at high doses, but there's not a problem with low doses. And that zone D had 30,000 people in it. And they actually had a lower leukemia rate than the people in zone C, closer to the blast, and the people in zone E, farther from the blast, which raises the possibility that at certain low doses, there is what's called a hormetic effect. In other words, a little bit of stress is good for you. A little bit of exercise is good for you, which is the low dose zone. But if you can exercise yourself to death, high dose zone. You see what I'm saying? Makes sense? And that's called the J curve. And that J curve is evident in the Hiroshima and Nagasaki data. And that was after surveying and studying 130,000 survivors. So it was an unfortunate but ghastly opportunity to have an experiment on live humans. And that was the result. And the same thing with the radium doll painters. You heard of the radium girls. The girls that painted like radium to make glow-in-the-dark watch dolls for World War I. Well, they would lick their brushes. They were told by the company, lick your brushes to make a point, right? Well, they got radium in their body. And everybody's like, oh my God, radium is giving people cancer. The people with the very, very, very highest doses got it because it does build up in your body. The radium, the material it does build up in your body. Since it does, it can radiate you from within, the same as polonium and cigarette smoke. Okay. And the girls that had the highest doses, of course, they did get cancer, but the girls with the lower doses did not. And that should be as well known as the scary part of the scary part of the story. And that's my problem with the media. And it's like that article you sent me, well, it says, well, uranium is radioactive for 100,000 years. So was your granite countertop. So was the potassium in your body. The point is to how much radiation, and can your cells keep up with the repair from the damage from the radiation? And in low doses, they absolutely can.
So let me ask this then, because somebody's going to, and it does ask, like, I'm the kind of person who, I have Fiestaware, the red Fiestaware dishes.
Oh,
that
cool.
Back in the, I don't know when, 1950s or something, they were super popular and that they were radioactive, right? They were found to be, So, I did buy a set and I kind of freaked out a little bit when I read that. I'm a product of,
Oh, hey, I'm laughing, but I'm not laughing at you.
You can laugh at
me. I'm laughing at the absurd situation we've gotten ourselves into.
But I want you to say these SMRs and these small modular reactors,
and
there's not going to be radiation. There's not going to be radiation.
There's not. I mean,
just make it clear, because we're talking about policy. We're talking about regulation rather, and why those studies matter. But we're not going to have it anyway.
But the small modular reactors are generation 3, the light water, the little mini light water reactors. Mm-hmm. They're generation 3+. What that means is passive safety and walkaway safety. And because it's small with a small core, it's not going to have a melt through. There's not that much water in it to begin with. And it cools itself by natural convection. All those reasons I mentioned, to where the safety zone is at the fence of the plant. And I have a drawing, if you can find it, it's really cool. It is a Gen 4 reactor in full meltdown on RTN, roadmap to nowhere, image 26. And if you can find that.
While he does that, so who goes to these regulators, these bureaucracies, and tries to change those policies?
Well, it's kind of a chicken and egg thing. The Nuclear Regulatory Commission is open to licensing molten salt reactors and these other designs, but for one thing, they need their scientists to study up on molten salt, but the only thing they know is light water reactors, number one. And so Congress needs to fund the money for the NRC to get educated on molten salt reactors. That's molten salt. As far as the small modular light water reactors, God knows what's going on with these people, but it's kind of like like Westinghouse has this big old 1,000 megawatt reactor, and they go, okay, we have a small little 100 megawatt reactor. It's the same design. We literally shrunk the thing down. Okay, here's 12 million pages to fill out and give us $1 billion. It's like, it's ridiculous. It really is just absurd. Yeah, this is a Generation 4 reactor or a small modular reactor in full meltdown. That's it. And it's provably true. You know, the bigger reactors with more water in them and with active external cooling, meaning municipal water and power, right? You might have a problem if you have an earthquake and there's no municipal water and power to cool your big old reactor. With a Gen 3 Plus reactor, the AP1000 we showed you earlier, just keep the water tank full and it's cool. With this one, you can literally have coffee with the neighbors, which is what this is. Like, oh my God, I melted down. There goes the bonus, you know, and the neighbors are over giving them coffee and donuts. That's it. Though that's your small modular reactor in full meltdown.
In your slippers.
Yeah, and they have matching happy face slippers. And that is what you would be confronted with in Cincinnati if you were so foolishly to get a small modular reactor. You'd have to make a pot of coffee for the person.
Yeah, and doggone watch that thing just do nothing.
And just watch that thing do nothing. Yeah.
So since we're having so much fun with the fuzzy slippers, how about some facts about why renewable energy might be insufficient for our needs moving forward? I think we touched on this a little bit.
Well,
I know you have a strong opinion.
Oh God, I have all sorts.
You have a whole book on it, right?
My third book, our third book. I apologize, Tim, and my co-author Tim. I did the second one myself, but we did the first and the third. And he's like the brainiac researcher, math guy.
What was his name again, Tim?
Tim Maloney. I could not have done the first and the third book without Tim. Could not have done it. He can wrap his mind around. He's the electrical engineer, retired, and he can wrap his mind around all this stuff. And I was just like, oh, really? That's a good point. You know, and so, yeah.
Very
so
good.
thank you, Tim. Anyway, nuclear versus renewables. You want a couple of talking points? It's passive energy harvesting, renewables, versus active energy production. Okay. Renewables are harvesters. They are not production systems. They don't produce. They harvest and export. This is an extremely important point. They do not produce energy, and the batteries that they charge, if they are dependent on the renewables, are as much dependent on favorable weather, not good weather, favorable weather. It can be a crappy day outside, but the wind blowing is favorable. You see what I'm saying? And so renewables are utterly dependent on favorable weather. Reactors don't care about the weather. Okay. Renewables have to have a full and expansive and continual contact with the environment, whereas reactors are largely and almost completely decoupled from the environment. They're a tiny footprint versus the hundreds of tens of thousands of square miles that a national renewables grid would need. Yeah, okay, German wind. Okay, that's an example right there. You have it, and this is a good point. You have installed capacity upper right, and then you have delivered energy along the bottom, right? The renewable industry routinely touts the installed capacity. So you say, hey, we just installed a 100 megawatt solar farm. Well, you're only going to get 20 megawatts out of it over the course of a year. So it's puffery. Okay. Reactors, nuclear doesn't have to engage in puffery because the difference between what you install and what you get out of it is about 93% or greater. So if you install a 100 megawatt reactor, you're going to get 93 megawatts on the average over the course of a year. Mm-hmm. You install 100 megawatts of solar, you're going to get about 20. And you better have some batteries. They all cost money. And Roadmap to Nowhere is a fun and entertaining, with simple arithmetic breakdown of Mark Jacobson's 100% wind and solar plan for the United States. So we just said, fine, we'll just nuclearize this plan and we'll compare the numbers and run it out for 80 years because that's how long a reactor lasts. So how many panels does he have to replace? You know, His national wind and solar program would have a pile of used panels every week that is tall as and as big, the volume of 432 Park Avenue. And I have a picture of it in here.
And they're not clean, right? These are not clean elements that we're using to make renewable
panels are pretty clean. They do have a little bit of lead and cadmium in them. In the volume that he needs to do his plan, it's a lot of pollution. And the thing is panels are way more expensive to recycle than to put in a landfill. So guess where they're going to end up? And when you're talking about, and I'm not exaggerating, his plan needs 9.66 billion panels.
So for clarity, the renewables roadmap, and that I did read the first chapter of that book. You offered that to me.
How'd that work for you?
What's that?
It was entertaining, and
it was entertaining, and it was excellent and very well written and very clear. Whose roadmap is it? Like, is it the U.S. government's roadmap? Or is it the environmentalists? Like, who is it?
Mark Jacobson is a professor at Stanford, and he is the champion of the idea of 100% wind and solar. He's been pushing this concept for years. It's been picked up, as you know, by cities and towns all over the nation, pledging to go 100% renewables.
Right.
So he is the one that is behind the meme. Okay. And we took his meme and we used his numbers to dismantle his program. And the way we did it is like, he never says how many panels you need. So we added it up, 9.66 billion panels. And the replacement rate is about 450,000 every day, including holidays, for freaking ever.
And let's just go and say that the infrastructure we have in place now for the combustible engine and for, oil, gas, energy right now, as we're largely doing it in the United States, the infrastructure doesn't need to change when nuclear energy takes, us presuming that nuclear power plants replace, carbon plants in the future, correct?
Well, they would replace the carbon plants. In fact, our idea is that we have thousands of gas plants and coal plants and hydropower dams that are being dismantled. Thousands of them. Okay. And
because of the renewables roadmap?
No. What I'm saying is we have hundreds of hydropower dams that are now being dismantled. And we currently have thousands of coal and gas plants, which are operating, but you could replace those power plants with nuclear. And one, the land is already zoned for power production. And two, it has a spur line. It has a transmission line to export the power to the bulk transmission corridor. Okay. So most of May Jacobson's wind and solar would have to be built in greenfield space and run new spur lines. They average about 25 miles long. Whereas we're suggesting take out coal and gas plants and put in nuclear plants, and they will have their own spur lines. So we're not adding to the transmission system.
Yeah. One factoid that came out of that chapter, that roadmap to nowhere, that chapter I read, was that the backup for the renewables plan is hydro, and that hydroelectricity.
It's really a cheat on his part. Yes,
exactly. But it doesn't hold water.
It doesn't,
because there's a picture in there of the water levels that are not the same. They're getting lower.
Yeah. Have you seen Hoover Dam lately? Number one. Number two, he lists our national hydropower dams as backup energy and backup storage. And if you look at his plan, it looks as if he has 2 grid weeks of power. In other words, we have to power the whole national grid for 2 weeks. We could do it, theoretically, with all our hydropower dams. Well, that's just completely not feasible. He has a half day. He has 14 grid hours of battery and a couple of other odds and ends. But basically, he has $1 trillion battery fleet, which will cost $4.5 trillion over 80 years. $4.5 trillion, you can install about 2/3 of our national nuclear fleet for just the cost of his batteries.
Yeah.
Okay. Another thing is he needs 32,000 square miles for his onshore wind and solar. He needs 39,000 for his transmission. New transmission, not existing, new transmission. We can use existing transmission with brownfields. In fact, Bill Gates's TerraPower reactor up in Kemmerer, Wyoming, he's swapping out an old coal plant and putting in a reactor. It has its own spur line already built with the rights of way already done. Right now, people hate transmission. In Iowa, it's against the state's constitution to proclaim eminent domain for a transmission right away.
For power transmission.
Yeah. So good luck building out now we did the math, arithmetic in the book. It's in the book. It's just arithmetic. He needs 39,000 square miles of land to put, I can't remember the numbers. Anyway, it's ridiculous.
Right.
It's just ridiculous. Yeah.
We need some lucidity out there, and hopefully with good messaging here, like you. So success stories. Actually, you know what? Back up. I heard you say this. You rattled this off on a recording that I watched of you. What would you say to the staunch environmentalists who are against nuclear technology right now? I heard you do this, and I liked what you said, and I'll give you a hint where you went with it was you were talking about nuclear waste that already exists that could actually still be used in a, I guess, slow nuclear reactor.
Yeah, well, the two big bugaboos the two big buttons they push is radiation is incredibly freaking dangerous. It's like some subatomic Death Star in high doses. Absolutely 100% no argument whatsoever. And the other thing they push is the waste. What about the waste? What are you going to do about the waste? Oh my God, the waste. Okay, there's a couple things about the waste. The most important thing about the waste, if Jerry could whistle up I have so many images. RTN figure 15, radiation and useful. That's roadmap to nowhere, figure 15. Here's the thing about the waste. First off, you have the misinformation that all radiation is harmful. So number two, the used fuel is dangerous and harmful and deadly until all the radiation is gone. Well, that doesn't happen for like 100 and 200,000 years. Therefore, it's a 100,000-year problem. Oh my God, that's ridiculous. How will we tell our ancestors not to dig here? Well, the first thing is you don't advertise it. So all this sign thing is like, well, don't advertise it. But anyway, no, really. But the image I wanted to pull up shows that after 600 years, all penetrating radiation is gone. What does that mean? Okay. That means that you can literally hold it in your hand. After 600 years, see the years at the bottom? The penetrating radiation, where it says the red line penetrating. There you go. The red line drops to the green line, which is at 2 megagrays per hour contact handle. You can contact handle it at 200, at 600 years. At 300 years, use a forklift. At 600 years, you can handle it with gloves. The point is that after 600 years, all penetrating radiation is gone, which means used fuel cannot zap you from a distance. You would have to get it in your body and keep it there. Well, how's that going to happen? Fuel pellets are insoluble and they're inedible, which means if you eat them, they'll pass right through you. If you grind it up in a powder, you just eliminate it. You would have to grind a used fuel pellet into a powder and snort it to keep enough of the material in your body for a long enough period of time to do you any harm. And this is at the 600-year mark. Okay. And so these deep geologic repositories that are, they're safe for 100,000 years. It's like, to us, it's performative and is being done it's bought into the nuclear fear, and it is assuaging nuclear fear by way overbuilding it. And good for them. They had to work with what they had to work with. But I think it would have been a lot cheaper to just educate the public, because it's just the simple physical fact of the matter that after 600 years, used fuel, you have to grind it into a powder and snort it.
So is there a way right now to dig up some of the already buried nuclear waste and use it in some of the newer reactors?
Oh, yeah. That's the thing we're getting to. So what happens is the way you can shorten that time period from 600 years to 300 years is you can take all the nuclear waste. It's only waste if we waste it. Because what it is it's fuel that can be used in a fast neutron reactor. So your light water reactors are slow neutron reactors, and they'll fission uranium and some plutonium just fine, but they won't fission like the plutonium-243 and the americium-241, the stuff in your smoke alarm, americium-241, and these other things that are produced in a reactor in the process of making fuel. So these things are radioactive for a very long period of time, which means they're not very radioactive because any atom only has X amount of particles it could spit out. So the longer it's radioactive means the longer it takes to give up a particle or a bit of energy. So the less radioactive it is, okay? So anyway, the way you do this is you use a fast neutron reactor to put the used fuel in, and the fast neutron reactor can fission all the stuff that the slow neutron reactor can't. And when you do that, you can theoretically get up to 27 times the energy that you got out of it with a slow neutron reactor. Okay, so we have all sorts of fuel. If we just use the used fuel we now have that's in surface storage, we could produce enough electricity at U.S. current consumption rates until the end of the next century.
Wow.
Okay. Plus, there's 4.5 billion tons of uranium in the ocean. And one of my very best friends is one of the key chemists on the project to commercialize that. The Chinese have gotten it down to half of the price of marketed uranium.
All right. So that answers another question that a friend of mine posed to me was if we're going to run out of our uranium, but it doesn't sound like it. Okay.
Well, if you use all the uranium in the ocean, which is just a theoretical, let's play with numbers, we're talking about 240,000 years to power the entire planet, not just electricity, but every form of energy this planet uses in present time for 240,000 years. That's how much energy we have in the ocean.
Wow. Okay.
And my friend Steven is working on, not working on extracting it. We already know how to do that. Working on commercializing the extraction process. All right.
Okay. Yeah.
So here's the thing. We have a bunch of reactors we want to build, and a nuclear build out of small modular reactors, which is a little mini light water reactor. You need solid fuel. You need solid, fresh uranium. So even if we get all groovy and go Gen 4 with molten salt reactors, we're still going to have hundreds of regular reactors we have to fuel with fresh uranium.
Right.
And so seawater uranium will loom large in our legend.
Okay. Good. All right. We're going to run out of time. I'm already worrying here. I don't have any questions yet. I will get to questions if there are any. I'd like to. Nuclear energy success stories in the U.S. and France. I mean, France has been doing this forever, right?
Yeah, we had that France build-out chart. If he can find an RTN figure 37 is the build-out in France. Let's see, whistle that up. Yeah, France in the 70s and 80s, they took a 15-year period. They nuclearized 70% of their electric grid, 75% of their electric grid. Their electricity.
When was that? In the when?
Yeah, think about the mid 70s to the end of the 80s, somewhere around there. Yeah. And they built like 66 reactors. The way they did it is they picked a couple of designs and they kept building the same, that right there. They kept building the same reactors over and over and over again. Okay. That's that big build out. They took a couple of standard designs and they learned how to build them and they kept building them. And that lowers costs. There was a big study done by about 20% over the course of the build out. and they were built on time and on budget because they knew what the hell they were doing because they did it before. Example, go buy a dozen whatever from IKEA, time yourself assembling the first one and the second one, and then time yourself assembling the last one. It's all these are big IKEA. It's just like, these are just big things, and you learn how to build them, and then you know how to build them. It's just, I spent my life being a contractor. I'm not a scientist, I'm a writer, and I'm a contractor, and it's just stuff, and you need to learn how to build the stuff. And it takes orientation, and it takes good tools, and it takes experience. And we had that, and we need to build it again. And again, as I said earlier, if we don't know what we're doing, let's hire some pros and watch what they do.
So nuclear energy success in the U.S. there are some. I think there's one in Ohio on the river.
Yeah, but they just haven't been
so few. Yeah, and
there's so few and far between, because what happens when the NRC came in 1975, they were supposed to handle nuclear safety. And you look at the nuclear bills that have happened since 1975, and the graph goes like this. Well, we're building reactors. Now we have the NRCs.
Yeah.
Well, I'm not kidding. I mean, Vogtle was the first thing we built in 40 years. Well, we didn't have anybody on that, nearly anybody in the project who knew what the hell they were doing.
It's a problem in the whole entire energy sector, really, because I saw a graph. It's been a while, but it was an organization. I got to think of who it was. Anyway, they had shown like literally project by project, and things get even, coal or maybe even, I don't even know about the renewables, but I should have looked at it before I did this. But it was pretty telling about how regulation just is almost designed to choke up this kind of progress. And it's
ridiculous, and especially on top of the fact that the Chinese and the Koreans are building to IAEA standards.
Yeah, that's a problem.
Yeah, they're building to IAEA standards, so it isn't like they're building down and dirty and fast and cheap and bad reactors. No, they're
Tell me again what that standard is. Say it again.
IAEA, International Atomic Energy Agency. They were the people that monitor all nuclear activity around the world, or are supposed to, if the country lets them in to do it. But the thing is that China and South Korea are both fully on board. They build the reactors to total IAEA specs. The IAEA, they're kind of like, they just watch it, they don't blink. And they have all sorts of instruments, and they monitor stuff in real time. And you can't get away with anything. The only way you get away with anything is to get rid of them. And China and India and South Korea are like, yeah, come on in and watch over our shoulder. We know what we're doing, and we'll show you we do. And those reactors are fine. And the South Koreans are building reactors in country for about 3,300 a kilowatt installed. Vogtle was 16,000 and a kilowatt. And the two biggest reactor companies of the world, CNNC, which is Chinese nuclear, whatever, and EDF in France, they got together and came up with what they call the Blue Book. They surveyed reactor costs, production time, blah, 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 and they say that the standard around the world price should be about $4,500 a kilowatt hour.
I'm just going to say that we cannot have our adversaries being better at this.
Well, yeah, exactly.
I'm saying it for our viewers. We can't. So
no, we can't just. I mean, it's not just a question of American pride. It's a question of American sanity and survival. Is you need to be able to produce gobs of clean power,
right?
Gobs of clean. Even if you don't believe in global warming, who wants to breathe all that stuff?
I gotcha. Yep.
There you go.
We can do better. We definitely can do better. So we're going to run out of time here. We're going to close this up here, but like timeline of where we may start. This is funny. I saw a Facebook post about an energy. I can't even remember what it was. And I suggested SMRs, these modular reactors, because I thought the technology was a little closer. And the response I got back was like this laughy face, because I apparently don't understand. I thought it was closer than what it was. So how many years are we talking before we actually start seeing?
Well, let's
I
see
guess,
the first four BWRXs, which is the Westinghouse 300 small modular, Westinghouse 300 megawatt small modular reactor, the size of a Costco for the entire plant. Okay, four of them are now are breaking ground now. One in Oak Ridge, one in Canada, one in Poland, and one, and I think maybe Germany. Not Germany. No, they're like nuclear is verboten. We like to burn brown coal. Yeah. Don't get me started on Germany. Well, okay, I'll tell you about Germany. Germany could have nuclearized their entire electric grid for 1/4 to 1/2 of the money they've already spent on renewables, and renewables are only 16% of their electric grid. This
wow.
is the kind of arithmetic,
Right.
not math, arithmetic that's in our books. I have over 500 endnotes in our in Roadmap to Nowhere.
I do have a question here that popped up. This person asks, it says, I read that Abilene Christian University in Texas has a permit to build a 1 megawatt prototype MSR that was supposed to go critical last December. Do you know the status?
I don't know the status of it, but I do know the guy that is working out it's so cool. Andre is working out their nucleonics, which is like where do the nucleons, where everything happens inside the reaction and that kind of. He's working on that. Abilene University, those guys are awesome, and me and Steven visited the site, and our friend Andre, he used to be professor of physics at the University of Austin. He's at home now in Oak Ridge, and he's working on their nucleonics. It should be in the next couple of years. Bill Gates' TerraPower reactor is a small modular reactor, 345 megawatts, is being built now. They're breaking ground now. So I think in the next 5 or 6 years, we should have a half dozen of them in operation. And of course, China is proceeding with their molten salt reactor in the Gobi Desert. They're already starting to convert it to run on thorium, which is groovier than uranium for a number of reasons, but it takes too long to read the book and you'll understand it. So yeah, it is proceeding apace. Watch the news is all I can say. It's happening.
Okay,
It should be happening a hell of a lot faster, but at least it's happening. But the big thing we have to do is we have to get people to understand about radiation and the waste and how it is an eminently, there's no place to put it. Yes, there is. Build another storage pad. What's so damn difficult about that? You can't transport it. Yes, you can. The transport cask can withstand the broadside of a locomotive running at 86 miles an hour with no leaks.
So education is vital in these next few years.
Exactly.
It's been important all along, but
well, that's why I wrote my books
now.
Because my books can be converted into textbooks or teaching aids and form a complete basic education on all this stuff.
Well, in my closing, I have you plugging your books. So it's www.mikeconleyauthor.com.
Right.
And you have 4 books listed there, if I'm not mistaken. Like 4?
Finished and 4 to be written. The first one is Earth as a Nuclear Planet. And that's the environmental case for nuclear power. And it goes into all the stuff about waste and radiation and fallout and all those hot button scary issues that people throw up, no pun intended, to dissuade people. So that's what that handles. And then the LNT Report is a companion book for Earth as a Nuclear Planet. And it's a deep dive into the history of how all this nonsense came to be, and the subtitle is How Bad Science Made the World Afraid of Nuclear Power. And so there's 3 chapters in the middle of Earth as a Nuclear Planet, and the LNT Report is kind of like a deep dive into that. If you want to get into how did this come to be? Well, I tell the story, and it's a wild story in the LNT Report. And then the third one, of course, is Roadmap to Nowhere, a reality check on renewable energy. And what we do is we take the most popular 100% wind and solar program, plan, proposal on the planet, the meme of all, the Goliath, and we basically dismantle it using its own numbers to show how it is ridiculous. And I invite anybody to read it and come to any other conclusion that we did, unless they are still thoroughly convinced that radiation is, oh my God. So then read the first 2 books, because we wrote the first 2 books as prequels, so we can get rid of all the scare stories, so we can concentrate on energy systems.
Right.
Okay.
Right. So there's one last question, and then we'll wrap it up. And I don't mind going a few minutes over here for this. Is there a place that we can watch the progress on the implementation of these builds of various nuclear sites?
I would, you can go to the World Nuclear Organization, WNA, the World Nuclear Association. Let's see. There's several. Of course, my brain's a blank now that you ask. Go to the terrapower.com, which is Bill Gates's build of his TerraPower reactor. You can watch that. Number 2, Google up the BWRX. The boiling is Westinghouse's 300 megawatt small modular reactor. Is these nuclear guys love their acronyms. The boiling water reactor, the 10th version. It's their 10th version of their boiling water reactor, the BWRX. And it's the Westinghouse. It's 300 megawatts. And there are 4 of them that are breaking ground now-ish. And you can watch that. And I have tons of links in my books, because Earth and Nuclear Planet is about 500 links, and Roadmap to Nowhere has about 500 links. So you got buku links. So you look up anything you want.
Are these all ebooks? Are they ebooks? Oh, you had.
And they are ebooks. Yes, okay. They are ebooks. Well, Roadmap to Nowhere isn't published yet, but so I would get Earth and Nuclear Planet, LNT as ebooks, and then you got all sorts of clickable links. You can check on anything we said. We don't want people to believe a word we say. It's just like, this is what we say. Here's the reference, and here's the arithmetic. And if you don't believe it, here's more arithmetic. And if you can handle decimals, you can get through all the arithmetic in our books. It is no more complicated than, well, I learned them in 5th grade, but now it's probably junior high. But anyway. I went to in fact, my 5th grade school was across the street from what is now the the NRC, the Nuclear Regulatory Commission, in Rockville, Maryland.
I'm not even surprised.
Yeah. Cosmic, yes, exactly.
I have to say, this was way more fun to talk about nuclear energy than I even expected it to be. So, thank you.
I got more. You're welcome.
Oh, I know you do. I know. Thank you for joining us. It was excellent presentation and our back and forth with you. I enjoyed it. And this recording of this webinar will be up probably by tomorrow. I don't know, tomorrow or the next day, at empoweryouamerica.org. And I thank you very much, Mike. And to the audience, thank you for joining us. Go out and empower you. See you tomorrow night.